people, which I really do encourage you to do, ask questions in the chat, ask questions to the lecturers as well. And you can also, after the lectures, attend the tutorials, which are at slightly different times, to discuss material and ask questions to the tutors. There's a question about whether tutorials will be recorded or not. They will be. Is that correct? Rakin, yeah. Okay. Yes, they'll be recorded.
I'm not sure though.
Oh,
I mean, we can.
Sorry. We're not sure. Never mind. I take that back. We're not sure. If there's great public demand, which you should let us know about, then we will consider recording them. Now, one thing I want to say is there are actually so many students of this. We were very surprised. We were very pleasantly happy to learn that there are so many students, that this thing is being done in a webinar format and not in a standard Zoom call. That means if you want to ask a question, you should write it in the chat or raise your hand. And at some point, someone will unmute you so you can ask the question. We have to do it like this because we're doing Zoom webinars. Okay. Okay. So there'll be a break at the end when you can ask more questions. Okay. And we'll handle all the questions then. Okay. Now, here are some words about the homework. Now, to learn physics, you have to do problems. Okay. So we are going to give you homework problems that you should complete. They'll be placed online on the first day of each new topic. And so, for example, the first one has been placed online today. There are 5 problem sheets altogether. All right. Now, each of these homeworks is due 1 week after the release, and you can submit them by a Google form link at the end of the problem sheet. So if you download the problem sheet, scroll to the end, there's a link to a Google form that you can use to upload your solution. Now, the point of this is that what you have to do is, if you want to get a completion certificate for the school, you have to attempt 3 out of the 5 problem sheets. Okay. So let's keep that in mind. If you don't want the certificate, it doesn't matter. You can do whatever you like. But if you do want the certificate, please attempt 3 out of the 5 problem sheets. Okay. Now the problems, they vary in difficulty. Some are easy, some are intensely hard. But really, do attempt them, and you can discuss them with other people as well. Now, one of the fun things about learning physics, or just anything in general, is discussing the topics with other people. Now, normally this is very easy to do in a physics school. However, we have this online physics school, which makes it a little bit trickier. So to try to encourage this, what we've done is we made a Slack channel and sent you the invite. So when I took this screenshot, it was only me in the Slack channel, and it was very lonely. I'm happy to say that already about 80 people have joined, and we've been chatting a little bit. You should join the Slack channel. It'll be great. And I want you to encourage us to use this channel to talk to each other, talk about the problems, work on the homework together, do things like that. And this thing about discussing with other people is a really fun thing. If you can, some of you are present in the same country as others, a lot of you are in Bangladesh, then you could consider viewing the lectures together in real life. That will make it more fun. Work on the homework together. Try to do these things together if you can. Okay. Now, okay, that ends the admin. And now I wanted to say a few brief words about physics before I hand it over to Ratul for the main part. So why quantum field theory? Why are we all here? Why are the hundreds of us here in this Zoom room learning about quantum field theory? So the basic fact is that quantum field theory is really the foundation of our most precise microscopic understanding of nature. Okay. So I will now just briefly tell you what are some uses of quantum field theory. What are some things you can do with it? So the first and maybe most obvious use of quantum field theory is high energy physics. So, it's sort of fun to ask the question, what is everything made out of, right? I am mostly water. Water is made out of hydrogen and oxygen. What is a hydrogen atom made out of? A hydrogen atom is made out of an electron and a proton. Okay, what is a proton made out of? Already it's getting a little tricky, right? It turns out a proton is made out of quarks, okay? And you can keep doing this. You can keep asking this question, what is everything made out of? And the answer to this question is something we understand very well. It is the standard model of particle physics. The standard model of particle physics describes subatomic physics in a very fundamental way, and it involves basically all these particles that are in this table, okay? To understand what these are and how they interact with each other, you really need to use quantum field theory. And this is the focus of this course. This course is designed to give you the tools to understand the standard model of particle physics. And at the end of the lectures, you will basically understand most of the things in this table. Okay. So this is the focus of this course, and this is the focus of many lectures on quantum field theory. But you might say maybe you don't care about high energy physics. Okay, high energy physics, it's annoying. You have to build the particle accelerators to study it. It's a lot of work. maybe you care about other things. So say you care about not high energy physics, but other more everyday things. So for example, some everyday things that exist in your house or nearby your house, or maybe in a nearby physics lab, are metals, which exist in your house, and superconductors, which are also kind of very ordinary things that you can find nearby. So it turns out that metals and superconductors are also described by quantum field theory. A metal is basically a bunch of electrons interacting in some manner, and the quantum field theory that describes them is called Fermi liquid theory. Superconductors are, this is a picture of superconductors, something very dramatic is happening when they superconduct. It turns out that superconductors can be thought of as being described by something called the Higgs mechanism. You've probably heard of the Higgs boson, and it turns out there's a Higgs boson in fundamental physics and high energy physics, but there's also a version of the Higgs boson in superconductivity. And if you want to study superconductors, if you don't understand why this is levitating suddenly, then you need to understand the Higgs mechanism. And finally, maybe you don't care about metals or superconductors, but you do care about water. If you take water and you boil it, and in fact, you increase the temperature and the pressure so that in the water phase diagram, you approach this point here called the critical point, and you care about the physics happening at the critical point in boiling water, it turns out this is described by a quantum field theory. In this particular point, it is called the 3D Ising quantum field theory. And why on earth water would be described by quantum field theory is a really fascinating question that I'm going to tell you about in my special lecture at the very end of this course. Okay, so this is just to say that quantum field theory is useful even if you don't care about high energy physics. And finally, quantum field theory is really quite shockingly useful. So you might care about quantum gravity. You've probably heard that quantum gravity is a really hard and difficult thing, and that's true. But it turns out that in some cases, something called the ADS-CFT correspondence tells you that certain theories of quantum gravity are in fact exactly equal to quantum field theories that live in one lower dimension. This is called the ADS-CFT correspondence, all right? And what that means is if you understand quantum field theory large enough, maybe you can understand quantum gravity as well, even though it's something completely different. Now, the most well-studied version of this correspondence involves something called SUN gauge theory. We are actually not going to talk about the ADS-CFT correspondence in this course, although I think one special lecture will discuss it. But we will learn about SUN gauge theory, which is sort of one side of this correspondence, okay? So the point of all this is to tell you that many different things in nature are described by quantum field theory. And in fact, you can sort of say something very general. In life, whenever you have something quantum, something where quantum fluctuations are playing an important role, and you also have some notion of locality, meaning that there are points that are close to each other, and the points that are close to each other talk to each other more than points that are far apart from each other, the combination of these two principles, in some very general sense, gives you something which looks like a quantum field theory. This is the basic idea. And this is why quantum field theory comes up over and over again in nature. And now you, at the end of these lectures, should understand the basic idea of how these ingredients work. Okay, that is all that I want to say about physics. Let me just briefly take questions for 2 or 3 minutes, and then I'll pass it on. Are there any questions? This is to also give us some experience with using the questioning system. Any questions? I'm not seeing any. Okay. There is one question asking me to elaborate on locality. So just very briefly, locality is such a basic concept that it seems a bit funny to give it a name, really, right? It's just the fact that in life, you know that certain points are close to each other and certain points are not close to each other. Certain points are very far apart from each other. Locality is just that idea that there's some notion of points that are close to each other and points that are far apart from each other. So it's just a very basic idea, okay? And it turns out, though, that when you impose that together with quantum mechanics, you end up with a structure that looks a lot like quantum field theory. Okay. There are 2 more questions I'll answer very quickly. Are there any use of QFT in quantum information science? There are. A lot of quantum information does not require quantum field theory, but a lot of very fancy things in quantum information, for example, sort of error correcting codes, which can be sort of understood with topological order, they do use quantum field theory in some useful way. Okay. So now let me now stop answering questions and pass it, because it's getting a bit late, and pass it on to Rakin, who will introduce our next lecturer. I will stop sharing now. Goodbye, everyone. You'll see me again soon.
Thanks, Bhav, for the very nice talk. Our next speaker and the first 4 lectures will be given by Ratul Mahanta. He did his PhD at Harish Chandra Research Institute in India with Anshuman Maharana, and he's now a postdoc at Winnipeg University in Canada. And he has amazing papers on arXiv. You're welcome to check those out. It's like, okay, a business proposition. And yeah, over to you, Ratul.
Thanks for this kind introduction and also for organizing this amazing school. I mean, thank you all the organizers. So I think I would be needing some permission again. No.
No, I already added you as a co-host.
Okay.
How will you organize the break? Sorry to interrupt.
Yeah, I will tell.
Okay, yeah.
Okay. So like now I don't know. It's already 20 minutes past, but okay. So I'll try to give a break from say Bangladesh time 8 to 8:10. Is that fine? Okay. And I will also take questions for 10 minutes in the first session and also 10 minutes in the second session. But maybe for the first session, maybe at some point I can stop and then take questions and then again continue, or I'll see. Okay. So there will be, me and Taushik will deliver lectures, what is known as canonical quantization. And then Nabil and Gonzalo will talk about more advanced materials. And I will take 4 lectures. And my plan is to introduce the subject in the first lecture with a discretized version of it, and then I will discuss classical theory of fields, symmetries, and other theorems. And in the next 3 lectures, I will discuss the free scalar and fermion canonical quantizations, but there is no hard fast break, like which lecture, like it can be 1 + 3 or 1.5 + 2.5, I'll see. Okay, so there are some references for my lecture. So there is a book by D. Francesco Matthew Sanechel. So that's on conformal field theory, but it has a chapter on quantum field theory. That's the chapter 2. And it's actually very nice, very detailed. And most of the today's lecture I will be following that. And also throughout, I will follow Peskin and Schroeder quantum field theory book, the chapters, second and third chapters. There is also an online resource. It's QFT1 lecture videos and notes by Ashok Shen. You can find it at ICTS website. So these are the sources where from I will be mostly following. But I would recommend for future exploration a book by George Starman. Okay, and I will start, but I think I recommend you to ask questions. Whenever you have questions, write down in the chat. Or the question answer chat box, and if something is related to notations or people can answer, they will if they want, they will answer. Otherwise, I will take all of them at the end of the session. Okay, so first thing is why quantum field theory. So yeah, so quantum mechanics can deal with a system of n particles, but n should be fixed. For example, you may know of solving Schrodinger equations for like n interacting particles, and they are the number of particles are fixed. But in nature, there exist systems where the number of particle is not conserved. For example, high energy collisions of particles which can produce new particles beside the colliding ones, or say a gas of photons. So these are certainly outside of quantum mechanics. So quantum field theory is a framework where one can model such systems of many particles. And also I would like to mention here, and we'll see later probably, the quantum field theory dealing with relativistic particle does not give rise to negative energy states, whereas the quantum mechanics of single relativistic particle has such states, in case you are familiar of this. So, okay, so QFT is a framework where one can model a verb system. Okay, so this is a motivation to do quantum field theory. I will start with discussing the notations. And conventions. Okay, so first of all, I will be using natural units. So consider this relation E equals to h cut omega. Maybe this is familiar to you. E is the energy, h cut is the reduced Planck constant, and omega is the angular frequency. And from here, you can see that the mass, the MLT dimension of this is m L square t to the power -1. And c is the speed of light, and its dimension is this. I will set c equals to h cut equals to 1. So I'll make them dimensionless. So this will be the conventions, and this is known as natural units. So this is known as natural units. And immediately you can see from the dimension of C that if you make C dimensionless, then length has same dimension that of time. So dimension of length is equals to dimension of time. And also you can see from this relation that this is also mass inverse. Okay, so then everything is consistent, or we can everything we can think of in terms of length scale or mass scale. It will be clear soon now. And the space-time coordinates, they will have a 0 and then the 3 spatial coordinates. So the time coordinate is CT, and then the position coordinate, but we have set C equals to 1. So it is nothing but T and X. So you can see that time and length is in the same footing. And I will also be using form momentum, which is now have zero component, and then the spatial momentum. And zero component is if you want to introduce back the dimensions, so it is E by C, and but in our notation it would be just E and P. Okay, so the metric convention, I will use a Minkowski metric, which is mostly minus, and this is a diagonal metric, and it's a mostly minus. I'll also use a lower x mu, which is given by this, and whenever there is a repeated index, they are summed over. So that is Einstein summation convention. So this is basically actually sum over nu, eta mu nu, x nu, but I will not write it every time. And you can see that this is because of this mostly negative signature, this is nothing but x0 and minus x1 minus x2 and minus x3. And similarly, you can define p mu, which is nothing but p0 minus p2 and minus p3. And the reason, like here I am talking about Minkowski metric, because I will be defining a scalar product for any two vector AB, which is given by eta mu nu, A mu, B mu nu. So the repeated indices are summed over again. And for example, x square, which is x dot x, is nothing but t square minus x square. X dot p will be et minus x dot p, and p squared equals to e square minus p vector square. So these are the dot product we will mostly need. And here you are familiar with probably these, so I will also state this. So if you restore the factors of C back, so this is what it looks like, but I will be using this like without the C. So C is 1. So that's the highest speed. Anything is below 1. Okay. So
sorry, Ratul, can I say one thing? In the chat, some people have pointed out that it's hard to, on some computers, the very bottom of the screen is blocked by the zoom controls, apparently. So could you maybe not write anything very important at the very bottom? Thank you. Sorry to interrupt.
Okay, I'll not write. Yeah, okay. So how far it is fine? Is this fine? Okay, I guess so. Okay.
Yeah, I can't tell because it's okay for me. But,
yeah.
So, but anyway, yeah.
Okay.
Thank you. Sorry to interrupt.
Okay, no, it's fine. Yeah. So okay, so these are about the notations and conventions, and the dot products written here. Here you will be seeing it mostly, and I will now start talking about the fields. So what are fields? They are functions of space-time. So we'll be dealing with scalar fields, which will be denoted by phi, at least in this lecture. There can be vector fields because it has a covariant for vector index, and etc. So I think Taushik will be dealing with the vector fields. So I will not talk about them. And for a field, there is a action functional. So given set of fields, you can compute a number, which is typically a real number. And this is by something like this, like a Lagrangian, which depends on the fields and its derivatives. And then you integrate over the space-time and you get the action. This can be break as dt and d3x and the Lagrangian density. So if you know from classical mechanics that the integral over the position space looks like a Lagrangian, because then the action can be written as some dt over a Lagrangian. So the curly L, I will although eventually maybe calling it Lagrangian, but this is actually a Lagrangian density. This curly L. Okay. So idea is given a action, so a set of fields which are functions of positions and time, you can compute this by evaluating the integral. And question is for which field this has the extremum value. So they are known as classical fields. So classical field configuration are those which extremize the action functional. Okay, so that's what you also know from your Lagrangian dynamics course in classical mechanics. But to understand more about fields, I will be considering now a two space-time dimension and discretize them. Idea is you will see that there are infinite degrees of freedom. And unlike the usual Lagrangians that we deal in classical mechanics. And we will also see the quantization procedure in this scenario. So consider two space-time dimension and a single scalar field phi. By the way, I have not discussed what is a scalar. Eventually, I will discuss what does it mean. And suppose the Lagrangian density is given by this quantity, del mu phi minus half m square phi square. So this is again contracted notations. This is nothing but eta mu nu del mu phi, and okay, maybe I should write the other way. Okay, so eta upper is the inverse of the Minkowski metric as a matrix. So it looks same. So same as Minkowski metric, but it's just eta mu nu inverse. So this can be written as a time derivative of phi square minus position derivative of phi square, because there is only two space-time dimension, one time and one position. So these are the this is the combination, and therefore the Lagrangian density is given as half phi dot square minus half del x phi square and minus half m square phi square. So in my notation, phi dot means del phi del t, and del x phi is del phi del x. Okay, So this is a Lagrangian density. The Lagrangian should look like dxl. So this should be the Lagrangian, and the action should be this. So we will discretize it. How? So we'll consider the position is a discrete space. So it has a set of points, basically x0, x1, and so on. So they are n points, but we'll also consider that they are periodic. It means that the xn is same as x0. So it is 1D periodic lattice. Okay. So if you think of that x is a set of points rather than a continuum, the L, which is dx over the density, looks like a sum. Okay, so let me explain various terms here. So basically, del x phi, this goes as phi n plus 1 minus phi n divided by a. I should say that a is the lattice spacing between the points. So this is the lattice spacing a between, say, x1, x2, and so it is constant. I am taking a as a constant. It is the lattice spacing. And okay, now maybe it's familiar to you, but because it looks like that there are a set of degrees of freedom, phi n, and they are functions of t. So n is the x index. So in general, any field phi xt, you can think of at each x, there is a degrees of freedom, which has a time dynamics. So that you can think of. And since x is a continuum, that's why there is a infinitely many degrees of freedom. And like here it is labeled by n because it is discretized, and here the number of degrees of freedom is capital N. So capital N is the number of degrees of freedom in this system. Okay, so you can manipulate this Lagrangian, especially you can have the square, you can evaluate the square, and you can see that finally there are some interactions. So I will write it here. So this is, okay, let me just, okay, yeah, I think that's correct. Okay, so that's how it looks like. And especially this term, which is a product of phi n and phi n plus 1. This looks like an interaction. So 2 degrees of freedom are interacting. Although we'll call it a free theory, it will be soon clear. So what is a free theory? Free theory will be if the quantum mechanics is free. So bunch of free harmonic oscillators, that we will see. So in position space, it looks like interacting, and that's what even our free scalar field theory is. But by free, we mean that how it, when we quantize, how it looks like. We will interpret it. The quantized system will also interpret it soon. Okay. So this is the Lagrangian I will be using. So one step I should mention here, that if you square this phi n plus 1, so there are terms which is like this, and but since there is a sum over n and it is a periodic lattice, this should contribute to, it is actually same as phi n squared, because it is a periodic lattice, and one sum is nothing but 0 over n minus 1, and we know that n plus 1 is identified with the 0 point. So that's what a periodic lattice mean. Okay, so there are n degrees of freedom, capital N. And it appears as interacting. And the Euler-Lagrange equation of motion, like any other classical mechanical system, is nothing but for each degrees of freedom, we need to compute these. So this is the Euler-Lagrange equation, set of equations, and this looks like as okay. So these set of equations are coupled because the nth equation, time dynamics for the nth degrees of freedom, not only involves that, but also the adjacent one. So it's a set of coupled differential equation. However, soon we will be seeing that it decouples as a harmonic oscillators. Here I have also used like these derivatives. In my notation, this is the Kronecker delta. So whenever R equals to S, it contributes. If R not equals to S, it is 0. Okay, so for this set of equation, I will now have a trial solution. So there are some few steps I will be jumping, but I will directly state the solution and check which is easier. So this is okay. So this is what known as discrete Fourier expansion. And it is possible because it is a periodic lattice. So the position index, which is sort of n, which has a Fourier expansion. And here also at this stage, I do not know what are the omega n. We'll plug this in the equations and solve it and see what omega k are. But I should say that there are two set of solutions. One is with e to the power minus I omega kt, Another one is e to the power plus I omega kt. And the proportionality constant n is, we'll fix it later. All I know at this stage is it's some function of k, and this can be taken out. For example, whatever you define ak and the coefficient bk, which are time independent coefficient, you can take out some factor nk. That's what it is. For later convenience, I'm taking it out. Okay, so phi n's are real. So this implies and I am also assuming that nk is real. That's what a specific constant I have taken out. So I will just assume that a real constant has been taken out. So it's, yeah. So that's the reality conditions of phi. So it states that AK and BK are related. In fact, they are just complex conjugate to each other. And now one should plug this trial solution in our equation. And immediately you can see here that the double derivatives, the time derivatives will act on the t-dependent parts. And there is no other derivatives. And you can see that it leads to this equation. It actually will tell what is the energy. By the way, since h cut is 1, omega k is same as energy in my notation. So it is this.
Bhaiya, I think some people have some questions if you're interested to answer, or should
Yeah.
we postpone it to later?
Okay, so one more line and then I should take the questions. It's better that I should take questions at this stage. Yes.
Should I read it out from the chat?
Yeah, that would be helpful.
Okay.
Please.
There is a question regarding, could you please elaborate on that expression starting with the second time derivative of phi? I think it's on the last page. Yeah. Yeah. The trial solution, I think that you wrote, I think that's the question. If anyone is interested to ask directly, you can raise your hand and we can unmute you as well. Okay, there is a raised hand.
Okay.
Yeah, I've unmuted.
Okay. Hello. Can you hear me?
Yeah, we can hear.
Okay, so actually my doubt is about the trial solution. Did you come with, like, did you wrote it by following any thought process on it, or just let's see what happens with this? In the sense that the expression seems very elaborate, so I wish some insight to get some insight from
Yeah,
that.
so one thing is that you can see that there is a Fourier modes of for the for n, like so k can be thought of the Fourier modes for n. So it's basically a discrete Fourier expansion, and since it is a periodic lattice, so small n are the x modes. So, and there is a periodicity, and that's why you can expand it in a Fourier expansions. You can see immediately. Okay, so first of all, some property you can check from here, which I was about to tell, but let me tell here. So you can check that these holds. So there is a periodicity, and that is because of this exponential to the power, e to the power 2 pi I kn by capital N. So because of this, plus minus both are allowed. So I need to add both the coefficients. In principle, one can ignore the second term first and do the sum for negative modes to positive modes, but I have stated here only the positive modes, and that's why explicitly I have incorporated n and minus n, because you can see that in this it is yeah, so this is this has n, whereas this has like minus n. It's effectively like that, but like yes, so that's what I can say, like it's a periodic lattice, but I do not want it to, because my negative of ends are not meaningful to me. Only I have defined positive ends, so I have only as it stands, these phi ends are defined for only positive ends. So that's what is meaningful, and explicitly I have taken out the Fourier mode. So this is nothing but Fourier expansion, I can say. Yeah.
Okay, thank you very much.
Yeah, and the t dependence can be seen from the like double derivative. But another thing is to just plug it in the equation and see whether it solves or not. And that's what is my claim, that it solves when omega k are related to, I mean, it is a very specific function. So that's what when it solves. Yeah. Any other question?
Yeah, you can raise your hand. Yeah. I permitted.
Hello.
Yeah.
Yeah.
So, can you please explain why in the solution of phi and p you have written that nk, why that amplitude n it should depend on k? I mean, like, can you explain the reasoning, like why it should depend on k?
Well, it does not depend on k because k is summed over. So it's
Yes,
like
yes.
if you integrate out something, it at n does not depend on n. Oh, which n? The capital N you are
Yeah,
saying?
that's the
Oh, okay. So one can actually, I should say, okay, so maybe I should define some AK and the factors plus some BK and the factors.
Yeah.
But but I can write it as some same NK and this. It's not a problem. Like you can always define you can pull out a k dependent constant, but I think you first define nk, and then like you take your choice nk, and then you can find what is the small ak, right? Since from the solution you know capital A, and if you know also nk, you can define small ak. And similarly, suppose bk works, and you know what is your capital nk, you can define bk. So it's a choice, like we'll see that why it has been taken out for some normalization conditions, but it was a possibility that you can take it out.
Yeah, no, that I understand why it has taken out, but my question is like why it should depend on the index k. I mean, like for each independent degrees of freedom, why that n should depend on k? Is there any reason that is always?
Oh, okay. So it is okay. So actually, you can take out a factor of 2, for example, which is independent of k. But we'll see that if we take this out, then for later convenience, I can say at this stage, like otherwise, many of my commutation relations when we will quantize will depend on the energy omega k. So yeah, so it's just a choice at this stage.
Okay, thank you.
Okay. It will be clear later. Actually. Any more question? Hello.
Hello.
Yeah. Hi.
So in the previous section of the notation part, you wrote an equation for the Lagrangian density. What is the
Hmm.
physical motivation behind writing that that Lagrangian density in that particular form? Yes, here. Before the
Okay.
discretization, you wrote the Lagrangian density in a particular form.
That's a good question. You will be seeing it later. That the here. Okay, so you'll see that we'll discuss Klein-Gordon equation, which describes relativistic scalar particle, and this Lagrangian actually leads to them. So at this stage, I cannot probably motivate in a better way. Only you can see that it's a nearest neighbor interacting Lagrangian. That's what you can see probably here. It's just an interesting Lagrangian. Yeah. Yes, please
Hello.
ask. Yeah.
I have a question, which is basically, why we are doing discrete approach as we are doing some field theory, which is continuum in nature, and in case of lattice, which is obviously discrete in nature, but we are doing a field theoretic approach. So why a discrete approach? Is it to consider finite periodic range or something else?
Well, so it's true that we will be more in most of the lectures, even in the second part and so on. I will be only discussing a continuum, but it is to give you an idea that there are there are many degrees of freedom, and what the free theory means. So it's also like the general procedure, like in the quantization will be similar. So we'll soon see that it represents a bunch of free harmonic oscillators when we quantize this system, and this should be the general scheme. So it's just to motivate the general scheme. Otherwise, I could have
So,
only,
So in case of tight binding approximation, as you just mentioned, so in case of dealing with the 2D or 2D or 1D Ising model, we can use that approach. It's basically like tight binding approximation, and then in case of field theoretic approach, we can just replace the summation with the integral part. And in case of field theory, we can treat it like this. But this approach is quite unclear to me.
well, so this is not the approach I will take when I will actually quantize the free scalar field or Dirac fields. So it is just to motivate, and many of the things what appears here, like it's from also condensed matter physics, as you said, like the number operator and creation annihilation operators and etc. will also appear here, and then I can easily motivate to the continuum case. So it's this. I think it's just for motivation purpose. This is not the approach I will eventually going to take for the free scalar and free fermion.
Okay, thanks.
Yeah. Thank you.
Okay, I think we can move to your lectures, and the rest of the questions we can maybe take at the end.
Yeah.
Again.
Good. Thanks for asking these questions. So you can see that there are two possible solutions for omega k, but we'll only restrict omega k as the positive square root. So it's just not to we'll soon interpret it as energy, and we'll see that only the at this stage, it does not matter because we have both omega k and minus omega k in the solution. So both appears, but once you take a convention that among these two, omega k, which one is positive, which one is negative, based on that you decide what is creation operator and what is annihilation operator. So I will just restrict it to be the positive square root. So okay, so this is as I said, just the motivation purpose. We found the classical solutions. We also found the frequencies, so we can write the solutions, and this is where omega k is understood as the positive square root of this quantity. Okay, so you can of course check a few relations at this stage that I will be using, but let me give you as exercise. So this you already have seen, and because of the property of cosine, this can be written for the omega k. And also okay, so whenever q is any other integer, in our case q would be nothing but again 0 up to n minus 1. Q stands for some k mode. So you can see that whenever q say 0 or plus minus capital N or plus minus 2n, then this quantity is nothing but equals to 1. So summing over 1 is this. But you check that in other cases, it actually vanishes. Okay, so for the quantization, I will be using the Dirac prescriptions, which states that promote AK and okay, first I will promote them as operators. So this will be some AK and AK dagger, and therefore phi n are also operators. And we will be using the Dirac's prescription. But before that, I need to state what is the conjugate momenta. So conjugate momenta from the Lagrangian dynamics, you know that this is this, and you can see from the given Lagrangian that this is nothing but this, and from our expression solution, you can see that okay, so this is conjugate to phi n t, the degrees of freedom. And the Dirac's prescription is that the equal time correlators, commutators are given by this set of relations. Okay, so again, I have set h cut to 0. So what's the idea? So we had a classical Lagrangian. We had its equation of motion. We found some trial solution that has some specific omega k. We promoted the coefficients as operators, the ak and ak star to ak and ak dagger. And therefore, the degrees of freedoms are now, we are treating them as operators. We computed the conjugate momentum and we imposed these conditions. These are commutators of equal time commutators of these operators. And we'll be imposing these quantization conditions. This is pretty, this is quite standard in the quantum mechanics. That's how we quantize a system. But eventually, we want to know that what are the commutators between AK and say AK dagger, or I should say. So these we want to compute. These are the things we want to compute. And these are from the solution, you know that these are just a set of constant, time independent constant. So since these are equal time commutator, we can use it at any time. And the trick we will be using at t equals to 0. The relation phi nt and the pmt, these will be computing at 0. And then try to invert these relations and get to know these commutators between AK and AQ dagger. And we'll see that why we have pulled out this K-dependent constant. Otherwise, okay, so let me state, this should be K, this should be the final result. And if we have not pulled out a specific K-dependent factor, there is a prefactor appearing here, which I do not want. So it's a matter of convenience. Okay. So how to invert these relations? The trick will be, whatever we will be using here is same as free scalar and free fermions as well. So I will elaborate it here, but I want to know if it is the break time or not. Like,
I mean, it's up to you. If you want, you can give a break. Or
okay, so yeah, maybe I should. Yeah, there are many things to state. So maybe okay, let me sketch and then I will sketch the idea and then I will we will have a break. Yeah. So okay, so phi n0 is okay. So the idea is you multiply phi n by some factors like these factors and do the sum over n. And I have stated you some properties here of the summation, which I will be using. And once you do that, what remains are the AQ and AQ dagger that will be remaining. And because the sum over n will give some delta function in K and Q, and the K sum will give you the okay. So this would give what? So this is nothing but yeah. So whenever okay, what are our Q values? Q can be, so we are evaluating it for a given Q, say 0 up to anything between these. So this sum, after if you sum over small n, it will be a function of small q. So what are the terms contribute? They contribute when k equals to q, or when k plus q equals to n. So I am not going through the details here, but using the formulas I have given earlier, you can actually find it out. Yeah, so the last term depends on Q. Okay, all the terms depends on Q, but the sum depends on Q, like which delta will contribute. For given Q, we have to see that which K will contribute. Either, so when Q equals to 0, so the first delta will contribute, and the contribution will come from in the sum when k equals to 0. And when suppose q not equals to 0, but some say some, I don't know, any number between say something 3, say, and then what will contribute is when k equals to n minus 3, this will contribute. So, but anyway, we'll don't need to think about them, because this will go away. So the first term will be important, and similarly one can find that this is nothing but plus some terms. Okay, so let me anyway write it. NK AK dagger delta K plus Q 0 plus delta K plus Q n. Okay, so one can finally one can see that we will get these relations, and then I will also stop. AQ is nothing but and okay. So why I am evaluating this? Because soon now I will be will be interested in commutation relations like this, and since each AK and AQ dagger are dependent on phi n and Pn. We know the commutation relations between them by Dirac's prescription, and we can use them. So knowing the Dirac prescriptions between the equal time commutators, we can actually compute the commutator between AK and AQ dagger. And if you carry out this process, finally what you will get is this. Okay. You can also see that AQ turns out to be 0, and AQ dagger is 0. And you can see that if we did why NK should be, we could have told that it's just some factor, but why we have chosen basically we will set in NK to be nothing but 1 by square root 2a capital N omega k, so that this relation becomes nothing but delta kq. So that's why I have taken a very specific factor out, and otherwise in terms of the capital AK and AK dagger, we would have different relations, but we have taken very specific factors out from them, and we finally get a relation which is nice. Okay, so these are the commutators between the creation and annihilation operators. And maybe I should stop here, and I can take questions, and then we can have the second session. Yes, please go ahead. Yeah. Can you ask the question, like, or maybe Rakin?
Sorry, I missed. Are you giving a break here?
Yeah, but I can take some questions and then I. Okay. So I should start by computing the Hamiltonian, which is this, like usual classical mechanics, and one can compute it. It is nothing but okay. But we know what are phi n and Pn, right? So yes, we know this, although it's the expressions at t equals to 0, but in general, we know how they look like in terms of the modes AK and AK dagger. There will be the exponentials of omega k, I omega kt term as well. And so substitute them Pn, okay, actually Pn and also phi n, and carry over the sum, carry over the sum. So you know that this has a sum over k, and also Pn has sum over k. So that's how it looks. And if you substitute them and carry the sum over n, you will get this. And we have the commutation relations, which tells that AK dagger minus AK dagger AK is 1. So if you substitute it, you will get nothing but our known harmonic oscillator Hamiltonian. So you can interpret it as in non-interacting, this is very important, 1D harmonic oscillator with angular frequency this, because we know given a k, we know what is omega k, and they are different, they are function of k, so you can compute that. So in that sense, it is a free theory, and since and that's what we will be calling free theory throughout the QFT course. And ground state will be defined as which is annihilated by all k, I mean nk. So these are the annihilators, and AK dagger are the creators. Why is so? One should actually, okay, let me also give you an exercise. So check these relations. So these will decide which is annihilator, which is creator. So typically these kind of commutation relations between the Hamiltonian and the operators will decide which one is annihilator, which one is creator. From this one can see that if start with ground state, if we apply AK dagger, and this is again an eigenstate of H, but with a like some energy value, and that is those are the creators. Yeah, so I will come to this point, but check these things. But before that, let me talk about the ground state energy. The ground state energy is this. And since we have written our Hamiltonian as this relation, whenever AK acts on the ground state 0, yes, whenever it acts the ground state 0, it will be annihilating it. That's our definition of the ground state. And only the last term will contribute. And this is some constant. And this is nothing but so this is the ground state energy, which is basically sum over this, and you can compute it. This is a constant, but we'll omit this term. Like we will define Hamiltonian as, well, here you can actually keep it, but in field theory we omit. So we'll just treat like this. Why so? Because to us, only the energy differences are important. So it would not matter what is the ground state energy is. So basically, this Hamiltonian will be using. Or every time you can count this constant, doesn't matter, because but this C does not have a physical significance, as we will be only interested in the differences in the energy eigenvalues. A general state, which is eigenstate of the Hamiltonian, can be written as acting the creation operators on the vacuum, and using the commutation relations of A, K dagger and H, you can eventually show that they are the eigenstate of the Hamiltonian with some energy, which is nothing but omega k1 kr. I am mentioning the C here also, but it is the old Hamiltonian. Keep that in mind, and then acting on this is C. This is equals to C. Okay, so keep that in mind, but you can ignore the C. So let me do one computation. For example, there is only one K, and we want to compute this K equals to 0. Okay, let us call the state as K1, omega K, AK dagger, AK. And by definition, this is this. And what we will be using always, we'll be using the commutation relation so that we can put the annihilator on the right. And once the annihilator is on the right, it will annihilate the vacuum. Only term that will contribute is the delta. And how the delta will contribute? Delta will contribute as AK dagger, and the delta K1 acting on 0. So sum over K will pick only the contribution from Ka, and therefore you get back the same state as K1. And so similarly, you can do the computations. I will also be defining a number operator which is this will count the number of particles, the excited, we'll interpret these energy differences as the particle, because we don't know what this Lagrangian represents. We want to interpret it that it is some bunch of harmonic oscillator, and which modes are excited? Only omega k up to omega k plus r in a state. So they are only excited, and these will count the number of creators in the state, or in a sense number of particles in the state. So n acting on some state will count the number of the creators. Okay, so there are oscillators which has energies, various energies. Suppose you specify one of the oscillator, and this is some level, say K. somewhere. So it's the energy is omega k, and you can define a state acting the same operator r times on this. So basically it's nothing but ak dagger r times. And this is allowed for fermions, it will not be, but this we'll see that this will give the Bose statistics. But here I just want to say that an individual operator has been excited. The energy of this state will be okay, ignore the C, although I'm writing. So, okay, so this is excited states of individual operators, but in general, you don't know which have been excited. So some bunch of oscillators will be excited. Will be excited. Yeah. So this is the general scheme. You can the main message is that Lagrangian decouples when you quantize as a bunch of free harmonic oscillators, and you can do this algebra, and this algebra will be same for like rest of the lectures. Like we'll be dealing with same kind of number operators and a dagger operator. So that's why it will be instructive that you check all the details here. So I said it as exercise 2, but you can take another exercise, which is say exercise 3, to fill the details what I have stated. Okay, now the main part, like I mean the original, I mean what we want to do here is the field theory. So today I will not be quantizing anything. I will, like in the continuum limit, I will just do the classical theory of fields first, and I will I don't know, I think I will not get time to discuss the Noether theorem today, but next day I will start with the symmetries and Noether theorem. But now let me talk about what is classical theory of fields. Okay, so in general, we will have a set of fields. Earlier, we had only one field, but each of them, you can think of at each position, there are some degrees of freedom, and they depends on, like say, for example, phi 1, Tx can be thought of some phi 1 degrees of freedom at each x, and they are function of t. Just you can think of like that, and there are many of them. Okay, so action will be given as in terms of the Lagrangian density, but you know, given a Lagrangian density, what is the Lagrangian? And these are local. I will not discuss it here, but it depends on at only one position x. So everything is computed in a particular position x, and then you integrate it out. So we'll be varying phi I. If you vary them, okay, so vary means okay, so given a profile, say field configuration, I mean here you need to specify all of them. You can compute this number. This gives you some number, some real numbers. Yes, they are real. So you can compute this. If I give you another functions to try with, in principle you can integrate and you can find the new numbers. And see, I am not in the action, I am not writing x dependencies because x is integrated out. It's a dummy index and you get another number. So idea is which field configurations phi I minimize the delta s, like minimize or extremize the action. So that's we are going to get. So this is the least action principle, and delta s can be computed as like the Lagrangian density is function of field and its derivatives. So this can be computed as these. By chain rule. Yeah. But they commute. Why they commute? Because okay, so what we are actually trying? We are computing the action in some say phi tilde x. So some earlier it was phi x. Now we are trying some different function. Okay, of course, set of functions, but it is infinite, similar to the old one. So some variations. So these are the variations, and you can see that the derivatives of these is nothing but so whatever these functions are here, the variations are here. So their derivatives will be there. So this gives me the delta of del mu phi tilde. I can call it variation, so I can see whenever I am writing variation, I am not giving tilde. So the variation of this quantity is nothing but they are local at each x. This is, yeah. So this delta and the derivative with respect to position commute, and what I will be doing, so I will do an integration by parts. So integrating by parts for the last term will give you this time delta phi I plus a boundary term. Okay, since, yeah, so if you expand this, you will get this term plus the term which has been written. So it's just integration by parts, and then you can ignore this term. So idea is, since this is a yeah, so this will be evaluated at the boundary only. And the idea is that when you this total derivative term, when you integrate, you have to evaluate it at the endpoints, like of the space-time boundary. So which are say even at t or x, so it's like say minus infinity to infinity, and also for t, it depends which integration you do first. But at this boundary, we are assuming that the variations are all zero at boundary, at space-time boundary. Boundary. So we are trying variations for which at boundary we keep the field same, but intermediate at any say tx, the field can change. This has really, a new field has some dependence, but only at boundary it is same as the old field. So these kind of variations we will be only considering. And therefore, delta S is this. So, we want to find the extremum, and therefore we need to allow delta phi I at any finite x, very arbitrary quantity, and we can find the Euler-Lagrange equation. The quantity in the integrand should vanish for each field phi I. Because we can vary independently. For example, in the variations, we can have some component for, say, first field, not the second one. So you have to try everything, and then we should find the extremum, and they are arbitrary, and we can find this as the Euler-Lagrange equation. So this will be the Euler-Lagrange equations or classical equations of motion for the fields. And the conjugate momentum. Okay, I'll take 5 minutes more. I will discuss the Hamiltonian and then stop. And it will be a good point because next time I can start symmetry. Okay, so the yeah. Okay, so what is the Lagrangian? This is the position integral of the Lagrangian density. And after integrating over x, you will find a function of t only. You can compute the conjugate momenta. Conjugate momenta are given by, as in classical mechanics. So I am not talking anymore talking about this curly L. Now I have usual classical mechanics, the L. So this is integral over d3x. And the conjugate momenta are defined as, I will denote it by pi, not p anymore, but pi. So this should be the conjugate momenta. And okay, in shorthand, as I have already defined dot, so it should be this. And you can compute this. This will give. Okay, so since these x are dummy indices, let me call it as prime. And then it has del phi t x prime, del phi j, del phi I. So this is t x prime and this is t x. What we are computing this. And then there will be dot t x prime. Okay, so I am treating the Lagrangian as a function of the fields phi j and their derivatives. So whenever I use chain rule, they are actually summed over j. Like I am not using writing the sum, but it's the repeated indices are summed over. And in this treatment, phi j and phi dot are independent. Therefore, this term will not contribute, but this will contribute us to some Dirac delta functions. They are symmetric, like you can also write x prime minus x, Dirac delta are symmetric, and you can carry over the integration And finally, you will find nothing but, okay, let me write del phi j. Okay, so this is our pi at t, and x. This is the conjugate momentum. Using this, you can actually define the Hamiltonian. And this is Hamiltonian will be some function of. Okay, so let me do it in a next slide. Okay, so like what we have some momentum, conjugate momentum for each field. We have the degrees of freedom. Degrees of freedom are, there are many fields. So there is a sum over I, and also degrees of freedom is x. So there will be an integral over x. So minus L of t, this should be our Hamiltonian, and you can compute it as, I mean, you can write it if you write the Lagrangian in terms of the Lagrangian density, you will see you can actually be able to define some Hamiltonian density as well. This is curly H, which is the Hamiltonian density. Okay, so that's the thing. Like if you have a set of classical fields, like if you have a set of fields and you write the Lagrangian, you minimize, you get Euler-Lagrange equation. You can also define the Hamiltonian. And next day we will see what are the symmetry. Symmetry will be those transformations, because so such that the action is invariant. So this should be the definition of symmetry. Like again, x is dummy index, because x in action, x is integrated over. So what you really do, at each x you try a different function, you plug and compute the action and see that whether it's computing the same thing. And many often, not for the classical solution, even given a Lagrangian, you can see that there is a there could be a symmetry, and which, for example, take and also make it interacting, although Taushik will be dealing with interaction theory. But you can see that given a phi, if you compute this action, or if you replace phi x to negative of phi x, a different function which is just upside down negative of that, at each point, this computes the same quantity, because everything is squared in the action. The Lagrangian is such that phi square only matters, so, or phi to the power 4. So basically this is a symmetry. So we'll although this is a discrete symmetry, because it's not continually changed, the fields are all of a sudden upside down, so it's we'll be calling it discrete symmetry. But next time I will start with the continuous symmetry, and then we'll discuss Noether's theorem and then quantize the scalar field in the next lecture. Yeah. So I think this is a good starting point. And sorry for being a bit over time. So
Thank you so much, Ratul Bhaiya, for the very nice talk. I'll stop the recording.
you can